Asif, are you in a mute? We are not able to hear you.
Oh, no, I wasn't speaking. Can you hear me now?
Yeah, we can hear you. Sorry
So,
about that.
guys,
Yeah.
no, I was waiting for the paper to load. The YouTube to get started. All right. So we know what function calling is. We understand that you can use APIs and many things. Now let's read this paper. This is from Salesforce AI Research Lab, and it takes a very agentic sort of a core perspective. It says autonomous agents powered by large language models have attracted significant research interest. We know that. However, the open source community faces many challenges in developing specialized models for AI, for agent tasks, driven by scarcity of high quality agent datasets and the absence of standardized protocols in this area, which is a core problem, a practical problem people are facing. You notice that at this particular moment, there is a tendency to reinterpret open source, even when companies like Mistral, they release their models, they release the weights, they release the architecture, but never the data on which it was trained. So open source community has been facing a pretty severe scarcity of good training data with which to train models. And this is particularly acute in the space of AI agents. So this paper will make two contributions. We introduce and publicly release xLAM, a series of large action models. Now, notice the wording. They are calling it large action models. What is the difference between this and a LLM?
Action instead of language.
Yeah. See, in an action model, your basic approach is to have a thought, to think, and to act. Remember, one simplified way of looking at it is, if you remember the REACT paper that we talked about, REACT approach, which is foundational to all of this. We covered it in a prior session. Reason and act. So models which have been specifically trained to reason and act, right? And people are now coining a new term, large action models, models with only one particular focus. They're not saying that this model will do everything better than other things, but it says we will build models dedicated to this purpose, or fine-tune models dedicated to this purpose. And the way they do that is they take multiple approaches, which I will explain here. The xLAM series includes 5 models, both dense and mixture of experts. So and they base it on Llama and Mixtral. We'll come to that. What is a dense model? A typical large language model, when you think of, let's say, GPT 3.5, 4, 3, etc., these are, well, 4 we don't know, but to the extent that we know about GPT 3, it is just one large language, one transformer, isn't it? And that transformer has been trained with lots and lots of data. The problem with that is that given one model, let's say a transformer model, any input that you give, which is a prompt, it has to go through the entire, what am I doing? Sorry, I apologize. Yeah, it has to go through a signal transduction across the entire model. To the first approximation, the entire model does a forward compute on the signal, isn't it? It is FX on the entire model. So in other words, it will go through every single neuron that is here. Now, there may be some aspects, like some neurons may have dead weights, right? And because of that, they're basically transmitting nothing. But nevertheless, the machine has to do a forward computation on the entire input signal. So it's a full model signal transduction to produce the output. On the other hand, so these are called dense models, therefore the word dense. On the other hand, there is this paradigm, which is the mixture of experts. Now, I will not repeat this if you all can assure me that you know what this is, or I have taught you this. Anybody wants me to explain what mixture of experts is?
We are good as it. Yeah, we covered previously. Yeah.
We have covered. Anybody else? Prasanna, you look.
I saw one of your paper readings, so I caught up to that extent.
To some extent. Okay, I'll just refresh the memory a little bit. So imagine what mixture of experts says is have small experts. Let's say that you have, I'll just make it very intuitive, sort of. Let's say that there is a physicist, there is a chemist, there is a biologist, there is a mathematician, and there is a generalist. What you do is you forward any query to go, query I, to go through something called a routing network. By the way, this work, mixture of experts, was discovered by Hinton, Geoffrey Hinton, in a paper that dates quite a few years back, actually. I would imagine more than 7, 8 years ago, or 10 years ago. So what this paper says is that, see, you can have specialists, things, little models, which are good at their individual tasks. And then you can have a routing network, and you can train you can do this. You can do two things. In the simplest form, you can freeze this specialist. But in the more general form, you can co-train the specialist and the routing network. But let's assume the simple situation that these chemists are already chemists and the mathematician is already mathematician. Then what you need to do is just have this routing network given a query I, it just needs to determine which model is best for it, isn't it? So for example, if the query says, explain, so let's take something mathematical.
This kind of a classifier.
Yes, it's basically a classifier, right? So explain Atiyah-Singer index theorem. This routing network should immediately say, this one is meant for the mathematician, right? So the prediction of the model, the Y is which model, and you have to have Y hat. And all you can do is do a cross entropy loss, the standard, negative log likelihood loss, sorry, across the models, and make sure that the right query is being routed to the right expert, isn't it? So you can train your routing network. Do we see that, guys? This is straightforward, right? We can train the routing network. Right? Train so simple form. There are multiple forms of the mixture of experts. In the simple form, the experts are frozen. Train the routing network. Right? By the way, there is a lab on routing networks, on mixture of experts, creating a mixture of experts from scratch. I don't know if you have been through it. If not, you can ask me for it. I'll release the lab. So train the routing network. All it does is it's a classifier. As Prasanna said, it is a classifier whose only job is to tell which model to route it to, which model or which expert to send it to. Usually you don't send it to one expert, but you send it to two experts, usually. So you don't have one physicist and one chemist, you have multiple physicists and chemists out there, right? And then you take their responses and you ensemble over it. So that explains this sentence, which was a little bit packed. So I hope you have unpacked this statement now. So they have taken both the approaches. Trained using a scalable, flexible pipeline, and that part is important, that unifies, augments, and synthesizes diverse datasets to enhance AI agents' generalizability and performance across various environments. It is the core contribution of this paper, right? So they are saying they're doing two things. They're creating models, fine-tuning models, right? Both of the dense and the mixture of expert kind. And they are also creating a really good data set to fine-tune it, which was a huge contribution. See, what happened is that most people who were doing agentic reasoning or things like that, they would be creating data set only for specific tasks. One would be for coding, one would be for this, one would be for that. right? So they could train an agent, but it would be a LLM to act as a foundation for an agent. But that LLM would be good only at that sort of task. It wouldn't generalize beyond that task. And somebody else would have created another data set for another task, another data set. So for example, it's very, very common to fine-tune LLMs to do programming, right? And another to do something else, customer service or web shopping and so forth. And there are these little data sets. So one of the key contribution, which is, by the way, a huge contribution, because to create a data set which unifies all of them, cleans them out, and synthesizes and adds more. Synthesizing new data these days is, again, a pretty standard practice. To create one big standard reference data set for training or tuning action models is a big, big contribution. Actually, it is a lasting contribution because people are really, really hungry for such data sets. So then comes the results of it. Our experimental result demonstrates that xLAM consistently delivers exceptional performance across multiple agent ability benchmarks, outperforming GPT-4, Cloud 3, right? And notably securing the first position on the Berkeley function calling leaderboard. Who created the Berkeley function calling leaderboard? The Gorilla guys. Right? Remember, one of the contributions of the Gorilla paper was creating the function calling benchmark. They needed that to prove that their model actually does well. Right? By releasing the xLAM series, we aim to advance the performance of open source LLMs for autonomous AI agents, which is, of course, what this entire course is about. Potentially accelerating progress and democratizing access to high performance models for agent tasks. So, guys, you know what we are going to do. They are going to first, they put in a Herculean effort to create the data set. I can just guess. Obviously, I don't know these authors, but I can guess the amount of hard work that must have gone in putting all these data sets together, cleaning them out, doing. So let's look at the process. First, they take different data sets, they unify it, they do quality verification. Sometimes there are errors, lots of errors. Data augmentation, and sometimes what they do is data mixture. Mixture is what? You can change the function, the tool, when you list the tools available, you can change the order of the tools, you can change the instruction paragraph, where is it given, and so on and so forth. You can create various, to make sure that the LLM that you train is not brittle to just one format of data, right? You do all of that, and then you do supervised fine-tuning and DPO, SFT and DPO. So this one needs a little bit of a, by the way, what is BFCL? Can somebody guess? Well, we just talked
Is
about
it a classifier?
calling leaderboard. It's literally the Berkeley. So let's unpack this diagram. Berkeley function calling. Remember the Gorilla paper, what did it say? We created a leaderboard. We created a data benchmark. So that benchmark comes from your Gorilla paper. This is it, right? Toolbench is another. A web shop is a benchmark that is specific to, making an agent go shopping for you. Yeah, web shopping for you. Now let's unpack everything else that we have, like SFT. SFT, guess what it stands for, guys?
It's a fine-tune.
Supervised fine-tuning.
Fine-tune, yeah, supervised fine-tune.
Right. So let me unpack this. To explain this diagram, a little bit more is needed. See, so let's rewind back and zoom out and ask the basic question. And this is, of course, just to whet your recollection. How do you get a chat GPT, let's say from a GPT-3 or GPT-4, GPT 3.5 model? What is the difference? Right. See, a transformer, how do you make a transformer into something that you can chat with? Right. Given a transformer, you give it an X, it will produce a continuation. The decoder part of the transformer will produce a continuation text, or what you think of as input and response, input, prompt, response, right? This is what a transformer would do. Now, what you can do is you can use a causal loss, namely, suppose you say it was the best of times. It was the and you expect that it should produce, like from Dickens times, or simpler, more simple. The cow jumped over the moon. You expect the machine to say moon or the worst of times, right? So forth. So you can use a causal loss, like basically what is the machine predicting as the next token, compare it to what it should be, right? So suppose you expect worst to be the next token, or here moon to be the next token. You can look at the probability of the moon. What can you do? You can do negative log loss. That becomes your loss, isn't it? And so you can do very standard, your negative loss and so forth. You do all of that and you can prove. So basic architecture is that you can do what is called pre-trainer model. First stage is pre-training. That is easy. That is unsupervised. Even though unsupervised is in quotes, because what you really do is you scrape the web for all the text available, right? You know the answer. So the cow jumped over the answer, moon, right? The next token. And that becomes actually a class training this model. When you train it, you get a pre-trained model. People often look at it as the big monster. Why? Because is the golem. It has also been trained on a lot of toxic data. If you use it, it'll spew out hate speech, right? And things like that, and say all sorts of junk and falsehoods. Then you go through a process of supervised fine-tuning. So to illustrate that, let me give you an example. Suppose you were to say, what's the capital of California? You expect to hear Sacramento. You don't expect to hear an answer that says, what's the capital of Nevada? Right? But if you just do this pre-training, you realize that the world is filled with quizzes, list of questions. And so what is the capital of California often is followed by the text, what is the capital of Nevada? It could be. So supervised fine-tuning can help improve the situation, but more or less, you do this, and then the next thing you do, or in the original paper, which was the Instruct GPT, you did RLHF, reinforcement learning, using human feedback. So RLHF. And then finally, what you get is your chat model, or the LLM, what you typically call the LLM, right? So this is the process. Why do we need reinforcement learning? Because you need to align it with human expectations. Actually, the example that I gave, what's the capital of California, should be Sacramento rather than another question, can also be done through RLHF. You're saying align it to human feedback. Make it generate if you give it the same question, it can generate different answers, right? Every time you give it the same input, it will generate a different output. Why? Because there is a softmax here. You're sampling off the softmax, which means every time you ask the same question, it will give a different answer. You can take multiple answers, and then you can give it to human beings to tell which of the answers a human being would like. Given two answers, A and B, you ask a human being to say, this is better. A is better, right? And then you can use the data to do reinforcement learning. That was the initial way. The policy, if you're familiar with reinforcement learning, it was using PPO, right? Proximal policy optimization, which is a pretty common reinforcement learning technique. Then after some time came a landmark paper, which was the DPO paper. This is direct preference optimization. And that took everybody by surprise. What it said is, forget about reinforcement learning altogether. You don't need it. You can instead achieve alignment by preferences. It is the human preferences. You can align with human preferences without reinforcement learning using a bit of mathematical machinery. That is the direct preference optimization method you can use, DPO. And what it does is, you can say, how is that possible? How can I train it to align with human preferences without some sort of a reward policy, a rewarding system? Because reinforcement learning does reward and punishment, isn't it? A reward model. And then what this paper claims is that actually it is an implicit reward model in its own right, this approach, this mathematical approach. So a DPO has emerged recently as a go-to method for human alignment. And it is not reinforcement learning, though on a more colloquial way of saying it is that you're doing a DPO way of reinforcement learning, which is a bit of a contradiction, but that's all right. The main point is that it is bringing in the human alignment. So I hope now I explained to you this term, DPO. Now, what about full versus LoRa? Let me tell you what that is, full LoRa. What is full? See, suppose I have a model, a pre-trained model. And how can I fine-tune it? Suppose I have a data set, fine-tuning data set. What are the assumptions I have to make in the fine-tuning data set? Let's say fine-tuning data set has to be inherently something different from the data it has already been trained on, isn't it? Pre-trained on. For example, it can be your company's data. It could be your very specific use case data, as in this particular case. So the distribution, let's say that the original, I'm oversimplifying it, the original probability distribution of the pre-training data is this. And your data is slightly differently, like this. The distribution of your data. It has to be, it's a much smaller data, much smaller. So one way you can do that is take the pre-trained model and fine-tune, unfreeze the weight, the weights, the parameters, and fine-tune on the data, right? Continue training to get another model. It has its problems. The core problem is it takes a lot of compute hardware. Let's think about it. Suppose you have a 7 billion parameter model. A 7 billion, if you represent it in let's say that you represent it with 16-bit, that is float, 16-bit per parameter, which is still a quantization, but you don't lose much information. At 16 bits or 2 bytes, and with some overhead, you're taking about, a 7 times 2, that is 2 bytes per parameter, 14 GB. 7 billion parameters times 2 is 14 GB. Add some overhead, so approximately 16 GB. So just for inference, that is the forward pass, FX, because only weights are needed. You can get away with 16 GB. So your 4090 may be enough. But when you unfreeze the weights, what happens now? You go through the full model fine-tuning. You'll have to compute the gradient of the loss with respect to every weight, isn't it? That's the backpropagation, the gradient descent, because what is the gradient descent rule? In its simplest form, it's something like this, right? So you have to do something like this, and then you have to unfreeze the weight. So now you need another 16-bit, 16 GB to contain the weights, right? And it turns out that you have a quadratic term also. So another 16 GB. And so you're looking at 48 GB of RAM minimally to even fine-tune this model, even when you start with a tiny model like 7B, right? So it becomes rather expensive to train even a small model. And typically you would do it with, let's say, 70 billion parameter model or something like that. And that gets even more expensive, right? You can't do it on commodity hardware, the 4090s and so forth. You need more hardware. So one limitation of full fine-tuning is hardware resource constraint. But even if you had the hardware, there is another problem. And that problem is the machine, as you're training it on new data over and over again, you run a few epochs, there is a fear that the machine may conclude that this was wrong and this is right. The new data is the right way. And it may altogether go through a phenomenon called catastrophic forgetting. In which case, what will happen is it will lose its ability to do most things. The only thing it will be able to do well is your fine-tuned data, right? Which is catastrophic because the model has a lot of abilities and you don't have your fine-tuning data is only a small amount of data. So with fine-tuning, actually, it's a very dangerous task. You have to do it carefully, right? So people do all sorts of tricks. They may not unfreeze the entire model. They may unfreeze only some layers of the model and things like that, and work with that. So there are lots of, it's a whole field. I mean, let's put it this way. Because of all the risk and all the hacks that you need to do it carefully, fine-tuning is actually one of the highest paid jobs. Right? I'm told that in a leading company, a mid-level fine-tuning expert is paid somewhere in the somewhere north of 2.5 million a year. Right? It's that hot skill set. I suppose I'm making a strong pitch for my upcoming course. No, that wasn't the intention, but okay. So that is it. But so there is catastrophic forgetting and other problems. The other approach is LoRa. LoRa is you leave the big model frozen, and you train just two matrices, A and B. Right? These are called low rank adapters. And the intuition is, mathematical intuition is, that fine-tuning is just going to create minor perturbations of the weights, isn't it? At the end of it, fine-tuning means just a little bit of adjustment is needed to the weights to do well on this particular task, not to forget everything. So small perturbations, fine-tuning should cause only small perturbations of the weights. And those small perturbations, the hypothesis is it can be captured as low rank matrices. Or simply put, it could be represented with matrices, small, or simply put, it is represented by a lower dimensional space. Those perturbations can be represented or captured with vectors of a lower dimension, right? Representational dimension. So that's the main idea of LoRa. LoRa has been very, very successful. If you are into image generation, you know that people who do all this diffusion model and image generation, etc. Kids who don't know machine learning at all, they all know LoRa. Because there is a LoRa that will make your character wear glasses. There is a LoRa that will give them, I don't know, a particular look, right? There is a LoRa that will put, I don't know, that will add certain style to the picture. So you can have lots of LoRa adapters. And each of those adapters are small and they are highly composable. You can compose multiple adapters into one. And so your signal, your X goes through the full model, frozen model. It goes through your LoRa, and then it goes through a synthesis operation, and then finally goes to the softmax and the output. So That's your LoRa thinking, and it has evolved. The good thing with LoRa is you can train a LoRa on your local machine. Why? Imagine your 4090, it can capture your 7 billion parameter model. So 16 GB is used up, you still have 8 GB free, right? More than enough to fine-tune a LoRa model, a LoRa adapter, right? So you can do LoRa, and in fact, we do that in our course on fine-tuning. The demerit with LoRa, of course, is, you lose. If you could fine-tune the full model without catastrophic forgetting and having all the hardware resource, many people argue that that is the gold standard. LoRa has never achieved that same level of accuracy, but it gets to 90–95% of the result. Right? So, which is why LoRa is very popular. Anyway, I'm giving you all of this background to explain to you this initial diagram. And this diagram says it all. After that, you can realize that the rest of it is straightforward. Right? This other diagram is all that I will cover. The rest of it you can read. This figure says, look at what this figure says. An overview of xLAM model performances on the Berkeley function calling leaderboard. So what they did is they created a good data set to train the action model in LLM fine-tune. What LLMs did they take? They basically took the mixed trials and so on and so forth. And they, oops, sorry, what did I just do? They fine-tuned with that. So let's look at the results. The results are very impressive. The x-axis here is the model size. And you realize that this is a logarithmic scale, isn't it? 10 to the power minus 1, 0, 1, 2, 3. So at every step in the x-axis, it is 10x bigger model. On the y-axis is the overall accuracy of the model for performing the right actions, or basically knowing what is the right function to call. Right action is, in this case, right functions to call. Right. So observe something very interesting. Cloud 3.5 is at 75% accuracy. Gemini is at this. Then Cloud 3, Opus is at this, and GPT-4 is at this. These are the sort of the commercial or the frontier model performances. But look at how this xLAM is doing. I'll just color this. First, let's look at the frontier, the best of the xLAM, the top one. 8x22. 8x22B is a, what does 8x22 mean? It is a mixture of experts model. Each expert being of 22B parameter model, right? And 8 experts are there. This is a classic mixed-trial model, which has been fine-tuned. That model is of, look at the size of that model. At the end of the day, it's a 200 parameter model. It's big, it's relatively on the bigger side. Now, but look at its performance. It is, whatever you say, it is much, much, much smaller than GPT-4. And it is giving you better performance than GPT-4. Do you see that, guys? Right? It gives you higher performance than GPT-4. A smaller xLAM model, it's again a mixture of experts model. It's a 8x7B model. Look at its size. It's here. It's basically about 50 billion parameter model. 50 billion per 8x7 is 56. So let's say give or take 50. That is beating a cloud Opus, or even in the open source, a Meta 70 billion parameter model is beating, and it's beating cloud. Right. And now look at this. Much smaller single, not a mixture, but a dense models. These dense models are tiny, relatively speaking. And nevertheless, especially look at this model, the first one at the bottom. This model, which is just a 1 billion parameter model, outperforms Gemini 1.5 Pro, which is no joke, isn't it? So I suppose it brings home the point that in the space of actions, there is a huge scope for new work. These people have done, again, open the door. They have done groundbreaking work, and I'm sure subsequent work will be done. Clearly, if you look at the direction of this, you see how the accuracy of these models are going, isn't it? By size.
One question. So the topmost xLAM, right? It's
Yeah.
really big model. So
200 give or take 200 parameter, 200 billion parameter model. Yeah.
so it is a big model. I mean, model
180.
size is not where it's doing. It's just the accuracy is higher than the.
Very high accuracy. Yeah. But even as models, if you think about it, the model size of this, which at 180 billion parameter, is to the best that we know, way smaller than GPT-4. GPT-4 is rumored to be a trillion parameter model.
I see. Okay. So it's not even in this axis.
Yeah, it's not even in the, it's not even marked there. It is just marked as a line here, right? And it beats GPT-4, right? That's the point. That's the point. See, those frontier models, they never tell you, right, what's inside there, how many parameters they are. They're commercial models. They are very quiet about it. So that was the main point of this paper. So guys, we didn't get time to do SWE agent. We'll do it the next time because I noticed that we are running. I would rather take some questions now. If I do the next paper, it will take another hour, and I don't think I should. That would be fair at this moment. So, guys, are you? And the rest of it is mechanics, like how all the things they had to do to tune the model. But it's a good model, and the benchmarks are impressive. If you look at the Berkeley function calling benchmark, look at this. GPT-4 is the state of the art, which is a ginormous model. But look at how well xLAM does. xLAM at only 7 billion times 7 billion parameter comes practically at the same performance as this, isn't it? In fact, it begins to beat it in certain situations, right? In unseen categories. When you have data that's unseen, it really beats it. And when you look at the tools query test, it beats every commercial model, right? And likewise here, look at this, how success rate on the web shopping, it is on web shopping, a tiny model, xLAM, beats everything else, right? GPT-4 is quite a bit below that. Look at this, GPT-4. And then in tool query, look at this. It's pretty close, 0.75 versus 0.68, right? And you realize that with open source smaller models, you're competing against giants. So this is a David versus Goliath situation here. Right? So how can you be smart with smaller models? And this is a very good example of that. So I'll end with that, guys. There is one more thing, I suppose, figure worth talking about. They asked this question that, see, in training this model, we put a lot of effort in data augmentation and data cleaning. How worthwhile was that effort, right? So they say that if you just do raw data, you get this much of success rate. If you bring in data augmentation, you get 2.3% more. Let me increase the font size. 2.3% more. And if you do data augmentation and data cleaning, you get even more. And this is, by the way, a recurring theme these days. Especially look here. How much difference does it make? We are more and more realizing that data quality, the quality of the data with which we train this models makes a huge difference. In fact, if you remember, and this is a growing realization that one easy access is, see, if you look at the neural scaling laws, the 3 knobs you can turn to scale a model to do better models are more data, more parameters, bigger model, and more compute, more training. But now we know that there is actually a 4th dimension, a 4th knob you can turn, which is the quality of the data. right? And when you improve the quality of the data, it makes a lot of difference. If you remember the 5 series of models, for example, it started with the research paper whose title provocatively was textbooks is all you need. What are they saying? Because textbooks are really, really clean data, right? Textbooks are highly reviewed and carefully written. So they are as good quality text as you can get. And when you train a model with that, even tiny models like the 5 series, they do remarkably well. They're boxing way above their class. Okay. So that is it, guys. So I hope I am showing you where all this agentic stuff is going, and the huge emphasis there is to create dedicated models that do very, very well with actions, with function calling, with this, right? Agentic reasoning. So these are obviously the agent benchmarks. Okay? I didn't get time to do the SWE paper. It is there on your course portal. I will cover it the next time. Now, guys, xLAM paper, please do review it. But Gorilla, there will be I will have my team walk you through some solved problems with Gorilla as an example, and then give you homeworks to do on your own. Right? It's really worth it, guys. Do that. So that is it. I'll take questions.
Yeah, Asif, thank you. So I was holding it up one question. The stool bench or tool query, so the benchmarks, how that xLAM or Gorilla is been doing it. So if I'm writing a paper, or if I've been right, somebody actually who's doing research, right, the kind of the queries are the kind of the right searches I do it are the prompts I'm been giving it, and then which is where I'm being well trained my model is. So how do we do a generic benchmarking, or Berkeley is how they are making a general benchmarking across the function calling, and then right across the various models? Just I would like to get a right.
Is that two aspects to it. The Berkeley function calling is taking some of the leading APIs, right? Hugging Face and PyTorch, and a few others. The idea is that if you can train a model and to do well on these benchmarks, and they must be adding some more, but to do well on this, right? Then the hope is that that model can generalize and do well on other APIs too. Remember, when you train a model, you don't say that it has to be taught every single situation that it has to handle, because that you cannot. Then it will just memorization. You train it with a small part of the universe, right? And hope that the machine learns to generalize to the rest of the universe. Right? So once you have trained a model on some APIs and you notice that it is doing well on these benchmarks, the hope is that it has learned to generalize. And so, like in your document retriever or the RAD part, you can give it any other API, and then it should do well with that. In fact, there's enough evidence now because people have been doing this with great success. This thing, by the way, now is being used by every single leading, the Berkeley, Gorilla stuff is being used by all the leading companies. I mean, the people who are the frontier side, they're all heavily using function calling. It's become in 1 year the thing, right? One of the dominant ideas or things that are used in production, that's used heavily now.
Yeah, got it. Yeah.
Right. So if you're doing, Ravi, if you're doing agentic systems in-house, to not do function calling is it would be very odd, like if you are not incorporated that, because you can get so much power by doing that, isn't it? So,
Yeah. So actually I had a lot of struggle with right business proposal document, but finally I had a successful run after so much of effort.
yeah.
Certainly, this certainly would help, and then minimize the. I hope that I can generate even much greater in detail document compared to